for those of you guys just joining us, if you guys actually watch the videos and don't just shortcut the notes. But anyway, we just went over in the back of our homework spirals 52 to 55, and the kiddos took a picture and should be sending it to you. But otherwise, we are going to go grade before, volumes. We're going to grade homework 30, section 8.2. All right.
No, the streak broke.
For yesterday, though, I still give you a high five. But you have to start over again. Okay. It's okay. Don't be discouraged by it, Diva. You got this. Here we go. Section 8.2. Oh, look at all the pretty pictures. Oh, my goodness. Anyway, coming back. Whoop. Number 4. Oh, that's way too zoomed in. Hold on.
Wait, the screen is frozen.
Oh, let it go. Let it go. Okay. Why is this so zoomed in? Oh, it must be this kind of zoom. There we go. All right, number 4, final answer, 4/3. Number 24, final answer, 4. Sorry. Guess you guys have to skip around in homework. Number 4 is 4/3. Number 24 is 4. Number 52 is A. What? Is that it?
Yeah, we did.
Oh, 54. 54 is B. What's NINT? Function integrate using the integral function of our calculator. Okay. Okay, any questions? 4/3, 4, A and B. I'm ready. 4/3, 4, A and B. Oh.
49.
49? No. You mean 8.3?
Oh, 8.
It's okay. That's usually something I do. Yeah, it's due Tuesday. Okay. Lo siento. Give me 1 sec. Okay. 49. Anything else? We okay? Oh. Anybody want points for 49? If it's only one question, I can do it. And there are lots of people that are gone. Okay. That's totally an AP thing, so I'm glad you asked it. But yeah. Anything with a K, I get it. Let's go find him. Number, next page. Story of my life. How's it going? Richmond said, yeah, it looks fine. And you guys said you love it, so I can get pricing and we're good? Sweet. We're just going sweatshirts. Anybody want a t-shirt specifically? Okay. Want a crew neck and not a hoodie? Okay, so I'll ask for that. Esta. Such an AP question. Here we go. Okay. Find the positive value of K such that the area of the region enclosed is 2. Usually, for this one, the AP says set up but do not solve. Set up but do not evaluate. But anyway, either way, it's important to know what's going on. So, all right, our objective area enclosed 2. So what I see is the idea of top to bottom. We have to get our bounds. We could do our cosine of x minus our kx squared, but right now we are not taking into consideration orientation, top bottom. Has to be top bottom because everything is in terms of x. We're not going to get it in terms of y because we would have to use cosine inverse. No. And we know the area has to equal 2. This one says we should actually be able to find k. Now k is specifically a constant, true? So can't I technically pull k all the way out? Now I still have question marks on my bounds. We haven't even thought about those two, but technically we can say that. So technically we can divide both sides by k, but hold on. Doesn't it say enclosed? So if k is irrelevant, basically, right? to the bounds. K is completely irrelevant to the bounds. What should I be able to do off to the side? Now, over there a second ago, I was just looking at e, was it e to the x or e to the negative x? And 1 over x, and I was like, The graph really helped me, so I'm going to go ahead and try that here. For instance, we know that x squared is 0, 0. We know that x squared also goes through 1, 1, and 4, 2, etc., etc., etc. True? We also know cosine goes through the point 1, 0, 1, same height. And it doesn't touch down until pi over 2. Hold on, this is a 1, so pi over 2 would be 1.5-ish, right? Is that okay? Somewhere over here? Not 3 pi over 2, I apologize. I was thinking 3 halves because pi is approximately 3. So pi over 2 is 3 over 2, so approximately somewhere in between 1 and 2, yeah? So there's your cosine, and cosine will do the same thing over here. And then it cycles if we were to keep going with cosine. So where does cosine and x squared intersect? Let's think about this. What's going on in between 0 and 1? Something before 1. Cosine can equal things like 1 in between 1 and 0, square root of 3 over 2, square root of 2 over 2, 1/2, 0. Actually, I should pause for a second, guys. Was the k that was the answer? Is it a decimal or not? It is? Ha! Praise the Lord. What does that mean? I was quickly thinking, and none of those are going to come out. I mean, if it's 1/4, maybe. We're not going to be able to solve this by hand. So here I was. The graph still helps. You guys should get the graph in your calculators. And what are you going to do? Find A and find B. And who's A and who's B? Intersections. True? Okay. So then we can come over here. Careful, the AP can get mad at you because I just put A and then I'm going to put A again. So I'm going to get rid of that. So now I have A, now I have B, now I have A, now I have B. So can't we actually solve for this guy? So all we need to do is solve for that guy. We can move K over to the side if you want. Solve for that guy and set him equal to 2 over K. Or actually, maybe it's a lot easier too. Just solve for K. So we could instead say, since we can pull out K, K is going to equal 2 over that guy. Does that work? So you just find your intersections. You can stow them. We're okay with stowing still, right? We can stow the first intersection as A, stow the second intersection as B. There is symmetry, so technically I guess you could just find A and then make that negative A. That'd be awkward. A is a negative number. I guess you could find him and make him A and him be negative A. Anyway, ways to save on time. You get your intersections, you throw in. I put absolute value, but technically don't I have the cosine on top and the x squared on bottom? So I guess I'm okay even if you don't do absolute value. And then solve for K. Is that cool? Cool. Okay, let's go. Section 8.3. Accumulation, man, that word is following us wherever we go. Accumulation of infinitesimally thin slices. The impossible made possible. All because of the limiting process and the idea of infinitesimals. Do you have to draw the shapes? No. What's the idea? Finding volume of irregularly, shaped solids. Accumulate the slices. What's the idea? The accumulation is done by the integral, but we still have to, kind of like Justin was asking yesterday, we still have to define the parameter of each of the slices. And we can't individually define each individual slice because there are infinitely many. So let's not do that. Instead, let's put into an integral which can accumulate for us some sort of mathematical expression that based on a value of x would solve for the area of said cross-section. And all we have to do is add a little depth to that area, aka area of the base times the height is how you find volume. The little bit of depth is going to be our differential. Throw it in an integral. It does all the work for us. Or maybe we'll be doing the work, but the integration process will accomplish that accumulation for us, I should say. So therefore, quick reminder of cross-sections, which the AP can use. If so, it'll be maybe 1 or 2 questions. Cross-sections are just slices of 3-dimensional figures. And to some extent, there's a natural way of slicing and there's an unnatural way of slicing. To some extent, there's a natural and an unnatural way of slicing. However, the AP, and specifically I believe this book as well, are very helpful as far as giving us clues as in perpendicular to the x and perpendicular to the y. And yesterday, just really quickly with my illustrations of the shells versus the discs, I think a great way of remembering cross-sections and cross-sectional slicing, which also works for discs and washers, you can think perpendicular. Because you're always going to be slicing perpendicular to, now it depends on what kind of shape it is as to what you're slicing perpendicular to. For solids of revolution, you're slicing perpendicular to the axis of revolution. But for other types of solids, like this cone down here, not cone, I apologize, this triangular pyramid, he's not revolving around anything. So there is no axis of revolution. But there still is an axis that is through the center of the solid or of the figure. So we'd be slicing perpendicular to that. So cross-sections will be perpendicular to something, to some axis that they are symmetric about. And for discs and washers, it's specifically the axis of revolution. So just like we're used to having a solid being cut up into slices, integration's like, hey, give me the slices or define the slices for me and I'll put them together to make the volume. So practically speaking, what do? Practically speaking with area, we figure out the bounds, we figure out the orientation, or we say, forget it, I'm going to put absolute value, but we should still think about intersections just in case. Set it up and solve. For cross sections, once again, identify the bounds. Once again, set up your expression. But this time, we're not just doing top minus bottom, right minus left. That would be a linear measurement, and a linear measurement times a differential gives the linear one-dimensional measurement depth, which gives us area. But now we have to give it area with depth, which gives us volume. It's how to move between the dimensions. I'm not sure if we've talked about it in this class or last year. There's a very interesting baby little book called Flatlands. Flatlands, a romance of many dimensions. Super interesting. If you were in the first dimension, how would you be able to visualize the second? If you were in the second dimension, how would you be able to visualize the third? And we live in a third dimension, so possibly it's trying to broaden our horizons as to how we could visualize the fourth. Super interesting book. But integration totally builds on that idea of each of the dimensions is the previous, give it some depth. There's some humor in there as well. There's also a sequel called Spherelands. I'm not sure if I actually read that one. Heard it wasn't as good. But anyway, we have to determine the slice, and to determine the slice, we have to think about the figure, think about the geometry behind it, but it shouldn't be too much harder than what's the area of a square, what's the area of a circle, what's the area of a semicircle, what's the area. The worst it gets is an equilateral triangle. You could be super snazzy with special ratios, and 45s and 30s and 60s and the ratio between them, or you could just Google it and say, what's the area formula? But the harder part isn't saying what's the area formula, base times height, pi r squared, 1/2 pi r squared, square root of 3 over 4 s squared. Is that the area of an equilateral triangle? Anyway, the hard part is using the math that you've been given to define it and to get it in terms of a function. But set up your integrals and solve. So, slicing, I don't know if you guys need to write this one down. I say the words and in my head I visualize. It doesn't mean that it helps you guys at all. Remember that when you attach a dx or when you attach a dy, or you put an integral in terms of x or in terms of y, the differential does have a meaning. The differential is what technically is the delta x or the delta y that is approaching 0 to get those slices infinitesimally thin and make the integration possible. So we're doing the area, which has no depth, times dx. So in this case, we'd be going to, and I think I have it on the next page, this is more for visualization. We take the area formula, which does the two-dimensional slice that has no depth, that cannot be accumulated to make volume whatsoever. But once we put a dx onto it, all of a sudden we have a depth that's approaching 0, making them infinitesimally thin and accumulating perfectly. Anyway, super cool ideas, but it helps you just a little bit as far as which terms to get it in. But you guys know the AP and know these questions. Usually it's kind of obvious because it's like, I can't get y by itself. Okay, dy. I can't get x by itself. Okay, dx. But sometimes, just sometimes, you're going to have to change one f of x into f of y, and you're going to need to know when. So, this was the forever card from last year. Whenever you're slicing perpendicular to the x, you're slicing down, the area is down, and the area that's perpendicular to the x needs a dx or a delta x depth. It's very visual. It should visually make sense if you're a visual person. If not, okay, memorize. There you go. You see perpendicular to the x, you better make it dx. Now this starts to get interesting if you guys go beyond just x and y. Let's say we had figures that were tilted and were diagonal, that were skewed. Then maybe you could take an integral with respect to, thank you, something other than x and other than y. College stuff, don't forget. But I don't think you guys necessarily need to write down this box, because this box is just the book's way of saying, I think, what I said. Sketch a solid if you can. Sketch a cross-section if you can. Give the cross-section some depth. Think about its orientation and the depth you give it. Whether it's a cross, that'll be dx. Whether it's up and down, that'll be dy. Get everything in terms of what you need it to be in terms of. Figure out your bounds. I do that first, but either way. And then integrate, and specifically you're integrating the area of the cross-section as your integrand. But whatevs. So then we get here to a typical problem that says you have this bounded area between 3x plus 1 and the x-axis with the restrictions x is 0 to 4 and cross-sections of semicircles. What? I don't see cross-sections. I know. What have I sketched? Not the three-dimensional, but the two-dimensional base. This is just the base. Where does the third dimension go? Or how is it formed? By rotating? No. By coming up. Can't I slice this region at some arbitrary x value and have it come up into a semicircle because that's what they say is going on? This just defines the bottom. If you look at the bottom of a loaf of bread, most loaves of bread, I guess not sourdough bread. If you look at the bottom of most loaves of bread, isn't it a rectangle? Is it rectangular? No, it's not. Turn it the other way. Oh, it's coming up in that weird little like Humpty Dumpty thingamabob, right? Now, if that was a bit weirder, you're like, oh, it's a sphere. It's like a something. The bottom is this region, 3x plus 1 on the x-axis and 0 to 4. The top is coming up into semicircles, as they told us. Perpendicular to the x-axis, which is why I sliced it perpendicular to the x-axis. Sorry, I'm graphing in the third dimension, so everything's a little bit down, right? Everything's a little bit tilted. If I give this guy depth, you guys can probably tell from the way the functions are written, but remember, you can't always base it on that. What's my depth going to be? Dx. To give my area, my semicircle depth, I'm going to have to go along the x. So therefore, specifically, I'm going to go ahead and say, what are my bounds? X bounds, please. And x bounds are going to be x equals 0 to 4, just like they told me. And what's my area of a semicircle? There you go. Oh, 2r squared. Oh, never heard it said that way. Yeah. Or pi r squared over 2, or 1/2 pi r squared. Oh, just plug it in. No, r's not x. You can't do that. Okay. This is the most commonly messed up one. Who's r? Top minus bottom cut in half. Ooh, right? Top minus bottom cut in half. So in order to get, we have to get r in terms of x, or else we can't go there. A is in terms of r right now. Who's r of x? Well, r of x is going to end up being 3x plus 1. That's the top. Minus x equals 0. That's the bottom. So the distance is always going to be the y value, right? The y value of this function, which goes from here to here. The y value is the diameter, so just take that y value. And if it was, for any reason, cut off somewhere else, it might be like 3x plus 1 minus 1 if this figure didn't go all the way to the x-axis, but it does. Cut it in half. Since that's my r, I go and 4 of 1/2 pi who squared? R squared. I got it.
Wait, why did you divide r by 2? Because you found r and then...
My diameter was 3x plus 1. Not r, I took my diameter in half. Yeah. So be very, 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 very careful. If it was just set up but do not solve in a FRQ, box it and be done. But if it was a matching, there's no way they left it like that, right? So make sure that you would be able to properly 1/2 squared is 1/4 times 1/2 is 1/8. And last year, just where did this come from? Because with semicircles, you forgot top minus bottom is diameter. Radius, you got to cut in half. 0 to 4 left. How would you solve this by hand if you needed to? Oh, I guess you could do U sub. I didn't think about that. Or you could FOIL it, either way, U sub or foiling. Because du would be 3, so just offset by a 1/3 and you're okay. You guys have the idea? Why isn't homework due on Monday? Like cross sections, whatever, let's go. Last year, cross sections were its own section. This year, cross sections, discs, washers, all shabam, one homework. Oh, no, I think last year it actually was one section. I cut it up into 2 or 3 pieces. This year, though, it's one homework, so hence we're taking a couple days on it. Sound good? Oh, that's why this is next. Yep. So what's different if you're not popping up like a loaf of bread out of some base into some 3-dimensional figure? What if you're taking the base, and it's not really a base at all, and revolving it? What if you're taking the base and you're revolving it? And this somewhat answers Justin's question to yesterday. How can you take some irregularly shaped solid and mathematically define it? Maybe it's not defining it as a whole. Maybe it's defining it as being the revolution of some other figure, which you could measure the height of with one of those cool little tools that has the top and bottom and squishes. I don't know what it's called. But maybe you could measure the height. Maybe you could measure the across. Maybe you could scan it into a program, actually define the parameters of the boundaries. And you wouldn't have to necessarily think about it as a whole, but you could think about it as a cross-section revolved. I shouldn't use the word cross-section, I apologize. A region being revolved.